Hello everyone, it's great to be here. It's our first time in London and it's a beautiful city and we are very glad to be here. Thank you David for the opportunity to talk here. It's been an amazing event. So today we're going to talk about how we use Redis to achieve our business result to process more than 60 million messages a day. Right? So I am Luciano Sabenza. I'm a senior software engineer at Wave Mobile. I've been working there for about 8 years, and I was a speaker in at the Redis Conf 2018. You can check my talk on YouTube. There are other cases using Redis in our company there. And here with me is Felipe.
So hi everyone, my name is Felipe and I'm also a software engineer at Wave Global. So I have been working with software development since 2008, working most of this time with some JVM applications and other open source technologies like Redis. So moving on, let me introduce the company that we work for. We work at Wave. So Wave is a customer experience company and it's part of Mobile Group, one of the newest Latin America unicorns. So at Wave, we create experiences through technology to help our clients reach their customers. So one piece of this platform that improves the enterprise communication is our messaging platform. In this platform, you could send messages in a lot of channels like SMS, WhatsApp, Google RCS, and Apple Business Chat. So we send more than 1 billion of messages per month, and this message generates about 2 billion of events to be processed in our systems, including our Redis cluster. So let's see what we are going to cover today in this presentation. Today we will talk about our messaging use case, the problem behind this use case, how we solved that in the past, and how we're handling the same problem today. And after all, we will talk about our achieved results and our lessons learned. So let's get straight to the point and talk about our sending message workflow. So think about any other company that uses the Wave's messaging platform. They could send messages to reach out to their clients with some flight information or any other relevant communication. So as you can see in this example, our platform will receive the message and we will record this message in our servers. And after that, we will forward this message to the mobile network operator. The mobile network operator is responsible to deliver this message to the end user's cell phone. Usually, when the end user's cell phone receives the message, they send back a receipt. So this receipt is really important for us because it's the confirmation that the end user's cell phone receives the message and is heavily used in our billing process. So after that, the mobile network operator will forward this receipt to our platform, and we need to match this receipt with the original sent message so we can send this receipt to the original sent customer. So it appears easy, right? But why is this so hard for us? Fundamentally, our main problem remains on the amount of messages that we send every day. So think with me. We send more than 30 million SMS a day, and this SMS generates almost the same time of delivery receipts. So we needed to match these receipts with the original sent messages in almost real time. So our main problem remains on matching this huge amount of messages with consistency and in a decent time to notify our clients. So in our legacy platform, our processing time was really slow, impacting our customer experience and generating a big overhead in our systems. So as I said, we are a customer experience company, right? So this is a major point for us. That's why we decided to redesign our architecture.
But before we talk about the new architecture that uses Redis, it's very important to talk about our legacy architecture based on Apache Cassandra and on Q. So the flow starts in the blue square, that is our sending message platform. We will send this message to the MNO, and then we will save the message and send status on Apache Cassandra using a Q as the middleware. After that, eventually, in most cases, we take a few seconds or minutes, we receive the DR from the mobile network operator. With the DR, the delivery report or delivery confirmation, we match the message that we sent with the confirmation that that message was delivered to the cell phone. Right? Once the match occurs, we delete the key on Apache Cassandra, and then we send a notification to our old legacy monolith. Right? We will get back in this monolith to explain a little bit better about it, but it's important here to stress that we delete the key on Apache Cassandra. So every match, around 30 millions, generates a delete event on the Apache Cassandra cluster, and that's a problem. After we do the notification, this old monolith can do a bunch of things on this message. It has some refound logic inside the monolith. It has some old legacy reporter logic in this monolith, and it is also responsible to route the message to one of our internal systems that implements specific integration protocols like HTTP. There is one system that implements HTTP there. There is another that implements SMPP, which is a SMS protocol, and a bunch of other systems there. In this old monolith, there is also some legacy integrations directed to the customers, some customized integration. So this is the entire flow with the customers, with the delivery report being delivered to the customers. Well, this architecture is not really cool. There's a lot of problems there. So we have some couplings in this architecture. We have some flows that could be executed in parallel, being executed in series. And the most important for this talk, we had slow matching operations with slow transactions, and we needed to do some slow table scans on that Apache Cassandra cluster, right? Let's explore a little bit this drawback. So one of the problems of this architecture is the put and get overhead due to queue usage. So in some moments we might put the same messages in 2 or 3 queues, which is not good when we have our volume. So it grows very, very big, very hard. And the point that I want to focus here is about Apache Cassandra and why it's not the most suitable tool for this task here. Well, delete is not really efficient on Cassandra, and we had a bunch of deletes on that. And it's not efficient because it generates some tombstones on the cluster. So imagine a huge amount of tombstones in the cluster. It causes some overhead that causes some need to some operations to repair the cluster, right? So it's not good. We had a bunch of problems with the delete rate on Cassandra. Also, we needed to do some slow table scans in some situations that we needed to expire some messages. We needed to do through the table scan, which is not good by definition. And also, we faced some consistency problems. Like, in some moments, we might put a message in one DC, and then we have some delay to replicate it to another DC, which causes really hard consistency problems. We lose some information due to these consistency problems. So, in order to address these questions, we needed to build a new architecture that's based on streaming technology and on Redis. So let's review the new architecture. The new architecture is based on Apache Kafka as our streaming technology. So we start sending the message, sending status to Apache Kafka, and then we save the DR on Apache Kafka as well, right? This will allow us to break the old monolith logic in several new systems. So we remove the report logic from the monolith, and we remove the refound logic in the monolith. So these flows are now completely separated, right? So let's focus on the matcher system. The matcher system here is the most important point here. This matcher system is now based entirely on Redis. So we have now a Redis cluster, and this cluster is a master-slave cluster. We have master-slave here for fault tolerance. We use Sentinel to fault tolerance as well. And we have 3 instances, and we use Lua scripts to keep the consistency of the data. So we will get back about that later in the talk. So we once the match occurs, we delete the key on Redis, and it's not a problem in Redis at all. And we send a notification to our router system. So this router system has only the router logic in the monolith, right? So the monolith here is broken in 3 new systems: the report, refound, and the router. The router will route the message to one of our internal systems that sends forwards the message to the customer depending on the type of integration with that customer, right? We also created a 4 new system to replace the monolith, which is this last one here in the slide, which implements this custom integration with some special customers, right? So this is the entire new architecture. It solved our slowness problem due to Redis usage and throughput. So now we have consistency guarantees, and we have a very high throughput, as Felipe will say in the next slide. So this is basically solve our problem. Let's talk a little bit about the results we achieved and the lessons we learned during this solution implementation.
So as a result, we had a great improvement in our SLA. So we decreased it from minutes to milliseconds. And also, using Redis, we reached peaks of more than 2,000 of operations per second for each node. So also, using Redis, we need less than a third of the original Apache Cassandra cluster. So this is a relevant saving in our hardware and operation costs. And of course, using Lua scripts, we solved our consistency problems. So now, Luciano will talk about the lessons learned.
So we have some lessons to share with you. The first lesson is not about Redis specifically, but it's about general lessons. You probably have heard this before, but use the right tool for the job. So it will save you a lot of work, it will get better results, right? It will save you a huge amount of time. And that's what we did here when we created the new architecture. So we replaced the queue technology for streaming technology in this scenario. And in our case, we used Apache Kafka, and there is some good reasons for that. We can't discuss this here, but if you want, we can talk later. But anyway, the idea here is not the technology, but the idea, right? Also, the most important for this talk, Redis is much more suitable for ephemeral data with high throughput and high consistency needs than Apache Cassandra. Right, and we learned that, and it improved a lot our customer experience. Let's talk about some lessons specifically about Redis. This is a lesson that we learned in the early stages of this solution development. What we found, and we are not sure why yet, I will talk about how we did to solve it, but what we faced was, in high throughput, Redis eviction might slow down the application throughput, right? So Redis eviction, it's the eviction policy that is configured there to when we reach the max memory on that, Redis starts to delete some keys, right? In our case, we are not sure why, but in our case, even with the eviction policy configured, the application was still facing some out-of-memory errors. So we imagine that due to the high throughput, eviction policy on Redis wasn't fast enough. It's pretty clear in this graph. So the first graph here is the input versus the output on the Kafka topic. So the blue line here, it's the input on the Kafka topic. And the second line, the red line, it's the output, the consumption rate on Kafka. So, and the second graph here is the eviction rate on Redis. So as you can check here, when Redis starts to evict keys, the consumption rate on Apache Kafka drops at the same time. So this is because we receive some out of memories from Redis, and then we retry again to put the data there, and eventually it will work, but it slows down the consumption rate on Kafka. It generates some lag, which is not good, but we managed to solve this problem, overscale a little bit our Redis cluster, right? So what we did was we have that nodes on Redis. They have 30 gigabytes of memory, each one of them. And in normal, we have configured the max memory for Redis around 25 gigabytes. And in normal operation, we use up to 20 gigabytes of memory in each one of the instances. So we have a very high safety margin on our Redis cluster, and it worked for us. Another lesson that we learned is that the payload size matters much more on Redis than on Apache Cassandra. And why is that? Because Redis keeps all the data in memory. So a lot of big objects, and we have a lot of objects, will consume a lot of memory. What we did was optimize what we save on Redis. So we started discarding unused fields. So there were some unused fields in the object that we save on Redis. We discarded them. We removed some metadata from the object, and we also renamed some fields, length fields, this kind of things. We start saving on Redis a compressed JSON, right? All these changes allow us to save a lot of memory, as you can see in this number. So we decreased the average payload size from 3 kilobytes to around 1 kilobyte. And this drops the average memory usage on Redis in normal operation from 36 gigabytes to around 12 gigabytes. So this allows us to build that safety margin that I talked before. So take care what you save on Redis. And we did that, and it works great. So we finish our presentation here. And I don't know if you have time for questions, but anyway, thank you. You can reach us here after the conference.
Yeah, thank you.